Over the past century, physicists have been fascinated by the concept of black holes, with the idea gaining traction around 1916. These cosmic anomalies are among the most captivating and enigmatic phenomena we know, sitting at the intersection of vast gravitational forces and a peculiar invisibility to our comprehension. A black hole, potentially weighing as much as 2 to 4 million times the mass of our Sun, remains a mysterious presence in the cosmos. Despite decades of intense research, our understanding has expanded from little to no experience to gathering more information and making even more discoveries. A recent breakthrough achieved by Michio Kaku has revealed startling insights about the interior of black holes, which may challenge our long-held assumptions and offer new perspectives on the nature of these celestial bodies. This brand new information opens doors to deeper investigations into what may have been overlooked until now. Join us as we venture further into the fascinating world of black holes and uncover what lies hidden within them. Inspiring, but what exactly are black holes? Before getting into the most recent findings by Kaku, it's essential to revisit the basic understanding of black holes. While most of us have at least a general understanding of what a black hole is, there are still important aspects that remain unclear. In 1916, Albert Einstein's groundbreaking theory of general relativity predicted the existence of black holes. At the time, the concept was purely theoretical. It wasn't until around 50 years later that evidence was discovered confirming that black holes are real objects in space. This revelation came in the 1960s during studies of the bright star X1, a celestial body that emits X-rays. According to observations, these X-rays were not just randomly moving but were being pulled into an invisible, dense mass. This mass, later identified as a black hole, changed our perception of the cosmos. The discovery was historic, demonstrating that black holes were not figments of Einstein's imagination but tangible, elusive entities that warranted further investigation. As a result of this groundbreaking discovery, scientists worldwide began a global quest to uncover more about black holes. Their efforts led to the realization that the Milky Way alone may host around 100 million black holes. However, due to the challenges in detecting them, this estimate remains imprecise. Even though black holes are incredibly difficult to pinpoint, scientists believe that millions of these massive entities are hidden within our galaxy, making it even more important to comprehend them. The core concept: gravity in black holes. Black holes exert such immense gravitational forces that anything crossing their boundary is inevitably drawn in. The singularity is the point at which the rules of physics as we know them cease to function. To put it another way, black holes are like gigantic vacuum cleaners, pulling everything into them. One of the most frightening aspects of black holes is that if someone were to fall into one, they would gradually stretch out and become part of the singularity, their body shattered by the ferocious forces of gravity before total destruction. It's best to avoid getting too close to one. Despite being scattered throughout the universe, the nearest known black hole is nearly 500 light-years away. In 2021, scientists achieved a historic milestone by capturing the first clear image of a black hole, the M87 black hole. This achievement was the result of numerous nights spent taking photos and aligning them to produce a single, cohesive image. As more data was gathered, researchers discerned that black holes consist of 3 distinct layers, contrary to the common misconception that they are just endless voids. The first of these layers is the event horizon, which marks the point beyond which nothing can escape. Once something crosses this boundary, it is drawn inexorably toward the black hole. The second layer, known as the photon sphere, is where light itself gets trapped, unable to escape due to the powerful gravitational forces at play. Finally, there is the singularity, where all matter is compressed into an infinitely small point, a place where the very fabric of reality collapses, and all known laws of physics break down. What's even more intriguing is that each black hole is unique in its own right. While they follow the general 3-layer structure, their behavior can vary significantly. This makes them particularly challenging to study, as conventional scientific methods don't apply. Researchers are compelled to investigate these anomalies through indirect means, such as observing the radiation they release or analyzing the gas and dust swirling around them. Sending a probe directly into a black hole is futile, as anything that crosses the event horizon is bound to gravitate toward the singularity, where it is crushed into nothingness. This inevitable fate means that billions of dollars cannot be spent on probes that would meet their end before offering any valuable data. Consequently, researchers must study black holes from a distance. The formation of black holes. Theories about the origins of black holes suggest that they may form when massive stars collapse in on themselves. As a star burns through its fuel, it can no longer generate sufficient power to counterbalance the inward pull of gravity, leading to its eventual collapse into a black hole. If the star is massive enough, this process continues until the collapsing matter becomes a singularity. To further understand the nature of black holes, scientists from NASA focused on the center of the universe, particularly the M87 galaxy. There, they observed a powerful whirlpool of hydrogen gas spinning at mind-boggling speeds of 1.2 million miles per hour. The centrifugal force should have caused this gas to fly apart, but instead, it remained intact, suggesting the presence of a massive object at the center, likely a black hole. This object is believed to weigh up to 3 billion times the mass of our Sun. Rotating black holes and wormholes. Another significant theory was proposed in 1963 by New Zealand mathematician Roy Kerr, who used Einstein's equations to describe the behavior of rotating black holes. He argued that rather than collapsing into a single point, a rotating black hole forms a structure known as a thin ring. This rotating disk of matter, known as the ergosphere, is essential to understanding the breakdown of physical laws near black holes. Kerr's model also predicted the existence of an Einstein-Rosen bridge, a theoretical wormhole that could provide a shortcut through spacetime, potentially connecting distant regions of the universe or even parallel universes. To grasp the idea of a wormhole, it's important to understand the concept of spacetime as described in Einstein's theory. Spacetime is a four-dimensional fabric warped by massive objects, creating gravitational fields that influence the movement of other objects. Consider spacetime to be a piece of paper. If you fold the paper, you create a shortcut between 2 points. This shortcut is the essence of a wormhole, a passage through spacetime that could connect distant locations almost instantaneously. Although wormholes remain a theoretical concept with no direct evidence, they are a natural consequence of general relativity. However, wormholes are inherently unstable, meaning they would collapse quickly if created. Despite this, the idea of a wormhole as a potential gateway to different parts of the universe. The quest for a unified theory. For decades, physicists have sought a theory of everything, a single framework that unites Einstein's general relativity, which explains gravity on a cosmic scale, with quantum mechanics, which governs the behavior of particles at the smallest scales. The biggest challenge is that these two theories, while incredibly successful in their respective domains, seem fundamentally incompatible when applied to black holes. At the heart of this mystery lies the information paradox, a problem first introduced by Stephen Hawking in the 1970s. According to quantum mechanics, information about a system can never be truly lost. However, when matter falls into a black hole, it appears to vanish forever, violating this principle. Hawking proposed that black holes slowly evaporate over time through a process called Hawking radiation, eventually disappearing entirely. If this is true, then what happens to the information contained in the objects that fell into the black hole? Is it lost forever, or does it somehow escape? This paradox has fueled intense debate among physicists for decades, with many theories attempting to resolve it. Some suggest that information is encoded in the radiation itself, while others propose that it is stored on the event horizon, forming a kind of hologram. This idea is central to the holographic principle, which suggests that everything inside a black hole could be represented as a two-dimensional projection on its surface. Quantum mechanics and the future of black hole research. To solve the mysteries of black holes, physicists are turning to quantum gravity, a field that seeks to merge relativity and quantum mechanics. One promising approach is string theory, which proposes that all particles and forces in the universe are composed of tiny, vibrating strings. If correct, string theory could offer insights into the nature of singularities and the structure of spacetime within black holes. Another exciting development is loop quantum gravity, which suggests that spacetime itself is made up of tiny, discrete loops, rather than being continuous. This theory could explain what happens inside a black hole and potentially offer a resolution to the information paradox. The role of black holes in cosmic evolution. Despite their terrifying reputation, black holes may play a crucial role in shaping the universe. They are believed to influence galaxy formation, acting as cosmic engines that regulate the growth of stars and distribute matter throughout space. Supermassive black holes, like the one at the center of the Milky Way, emit powerful jets of energy that can impact entire galaxies, driving the evolution of cosmic structures. Moreover, recent studies suggest that black holes might have existed before the Big Bang, potentially serving as remnants of a previous universe. Some researchers even speculate that our universe itself might be the interior of a black hole that formed in a higher dimensional reality. If true, this radical idea could revolutionize our understanding of the cosmos. The search for answers. With advances in technology, scientists are closer than ever to unlocking the secrets of black holes. Future space telescopes, such as the James Webb Space Telescope, and next-generation observatories will provide unprecedented views of these enigmatic objects. Additionally, experiments in high-energy physics, such as those conducted at the Large Hadron Collider, LHC, may help test theories about quantum gravity and black hole formation. Some researchers even propose creating mini black holes in laboratory conditions to study their properties, though this remains purely theoretical for now. As our understanding deepens, black holes may hold the key to answering some of the biggest questions in physics. Do they contain hidden dimensions? Could they serve as gateways to other universes? Will we ever truly understand what lies beyond the event horizon? One thing is certain, black holes are far more than cosmic anomalies. They are windows into the most fundamental laws of nature, challenging our perceptions of reality and pushing the boundaries of human knowledge. The journey continues. As we continue our exploration of the universe, black holes will remain at the forefront of scientific discovery. With each breakthrough, we move closer to solving the cosmic puzzle they present. Whether through cutting-edge telescopes, quantum experiments, or new theoretical models, the quest to understand black holes is one of the most exciting frontiers in modern science. In the end, black holes are not just objects of destruction, they are also creators, shaping galaxies, influencing time and space, and perhaps even holding the answers to the deepest mysteries of existence itself. The journey to unlock their secrets is only just beginning. Uniting gravity with quantum mechanics is required to develop a complete understanding of the universe. This theory, often referred to as the theory of everything, is a quest pursued by numerous physicists, including renowned scientist Michio Kaku, for many years. One promising candidate for this theory is superstring theory, which suggests that subatomic particles are actually tiny, vibrating strings. According to the theory, these strings create the fabric of the universe, explaining not only gravity but also phenomena surrounding black holes and wormholes. However, superstring theory also requires the existence of supplementary dimensions of spacetime, so small that they are impossible to detect with current technology. Despite the challenges, the pursuit of comprehending wormholes, black holes, and the fabric of spacetime continues to captivate scientists, offering the potential for groundbreaking discoveries that could reshape our understanding of the universe. Expanding from our current understanding, the pursuit of superstring theory and other theories that aim to unify the fundamental forces of nature remains an ongoing challenge. However, it holds the promise of unlocking new insights into the very nature of reality itself. These theories propose that the universe is composed of more than just the usual three dimensions of space and one of time. In fact, they imply that additional dimensions exist. However, these dimensions are so small and compact that we are unable to observe them directly with current technology. Their existence, though, could provide the key to understanding phenomena such as black holes, wormholes, and the deepest mysteries of the cosmos. Superstring theory presents an astonishing depiction of the universe, proposing that all matter and forces are manifestations of tiny vibrating strings. These strings can vibrate at various frequencies, with each vibration corresponding to a different particle, similar to how a guitar string produces different musical notes depending on how it vibrates. The fundamental particles of nature might correspond to different patterns of vibration produced by superstrings. If established, this theory would not only provide a unified explanation for the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, but also open up entirely new ways of understanding the universe's structure. This could possibly provide solutions to some of the biggest questions in physics, including the nature of dark matter and dark energy, which together account for the vast majority of the universe's mass and energy but remain largely mysterious. Yet, despite its elegance and promise, superstring theory remains unproven. One of the major obstacles to testing the theory is that the additional dimensions it predicts are so minuscule that they are beyond our current observational capacity. Detecting these dimensions would require instruments of unprecedented sensitivity and precision, and even then, the evidence might be indirect. This makes superstring theory a challenging subject to test through traditional scientific methods. However, its mathematical beauty and coherence make it one of the most compelling ideas in theoretical physics. At the same time, scientists are also working on other methods that could lead to breakthroughs in our understanding of black holes. Quantum gravity, for instance, is another field of research that seeks to combine the fundamentals of quantum mechanics, which govern the behavior of subatomic particles, with the theory of general relativity, which explains the behavior of large objects like planets, stars, and black holes. The hope is that by merging these two theories, scientists can gain a clearer understanding of how gravity works at the quantum level and, in turn, deepen our knowledge of black holes and other cosmic phenomena. The intersection of quantum mechanics and general relativity is crucial when studying black holes, particularly near a black hole's event horizon, where gravity is extraordinarily intense. This demands a theory that accounts for both quantum and relativistic effects. In fact, the interior of a black hole, where the singularity exists, is one of the most puzzling and extreme environments in the universe. The singularity is a point where space and time become so warped that the usual laws of physics break down. Understanding what happens in such a place requires a theory that can reconcile quantum mechanics and general relativity. This challenge has led to the development of concepts like loop quantum gravity and other quantum gravity models, which aim to resolve these inconsistencies and offer a more complete picture of black holes. As we continue to explore the mysteries of black holes, one thing is certain: the more we learn, the more we realize how much remains unknown. Black holes are not just points of destruction but also places of incredible complexity and potential. Some theories suggest that black holes may act as gateways to other dimensions, while others propose that they hold the key to understanding the deepest secrets of space and time. Regardless of their exact nature, black holes remain an important field of study. As our instruments and theories evolve, so too will our comprehension of these mysterious objects. Looking ahead, the next major challenge will be refining our methods of observing and studying black holes. One of the most exciting innovations in recent years has been the detection of gravitational waves. Gravitational waves are ripples in spacetime caused by the acceleration of massive objects, such as merging black holes. By detecting and analyzing these waves, scientists can learn about black holes and other celestial objects in ways that were previously impossible. Already, the detection of gravitational waves has provided groundbreaking insights into black hole mergers, and future experiments are likely to yield even more information. In addition to gravitational waves, another promising area of research involves the use of advanced imaging techniques and telescopes. The Event Horizon Telescope, EHT, which produced the first-ever image of a black hole in the M87 galaxy, is a prime example of how innovative technology can shed new light on black holes. By combining data from multiple radio telescopes worldwide, the EHT was able to capture an image of a black hole shadow, providing an unprecedented glimpse of one of the universe's most enigmatic phenomena. As technology continues to improve, we will likely be able to observe black holes in even greater detail, revealing more about their structure, behavior, and role in the cosmos. The study of black holes is not just about understanding these mysterious objects in isolation, it is also about deciphering the fundamental workings of the universe itself. Black holes play an essential role in our understanding of spacetime, gravity, and the very nature of reality. By studying them, we are not only uncovering more about black holes but also about the fundamental laws governing the universe at its most extreme scales. In conclusion, the study of black holes is one of the most thrilling and challenging fields in modern physics. With each new discovery, we inch closer to unraveling the enigmatic nature of these cosmic giants. Whether through research on gravitational waves, advancements in imaging technology, or the development of new theories, black holes continue to captivate both scientists and the public alike.